Limit theorem has to do with samples versus population and how the standard deviation changes because of it being a sample. Okay, that's really what central limit theorem is all about, and it talks about how to make predictions from a sample based off of the information that we have. Okay, and that's what this says. In 6.2, when we were working through these problems, we were working with populations. Okay, and so there's going to be a slight little change when we work with a sample. And most of the time we are only dealing with a sample because it's really difficult to survey an entire population. It's much more convenient most of the time to take a sample of that population. When we're dealing, again, what I've been saying, when we're dealing with a sample, our calculations and the properties change a little bit. So I'm going to go over some properties with you that you're going to need to know and show you how the calculations change. I will say that I'm not going to go into great detail about how the calculations change. If you want to find out all about that detail, it is all in the book explained in a couple different examples. Here are some properties that we need to know. If you want to take a picture, there's going to be two properties on the screen. So if you want to wait until I put both of them up to take a picture, please do that. If you would prefer to take a screenshot from your book, I've included the page number since it might be a little cleaner for you than trying to take a picture of this screen. Is anybody going to write it all out? Okay, just checking, trying to decide how fast I can. All right, so the mean of the sample means. So here's what happens when we deal with central limit theorem. We're going to look at several different samples, and you're going to find the mean of all of those samples. When you take the mean of those sample means, that ends up equaling the population mean. Okay, that's what this. Again, let me say it one more time. Oftentimes, from the sample, we'll take a mean of the sample. There's more than one sample most of the time that is taken. So we take the mean of each of those samples and then take the mean of those means. That will equal the population mean.
That seems like a lot of work.
It's very convoluted, and there are examples in the book if you want to look at it. You don't have to do any of it. I'm just explaining to you what it's all about, what the properties are. We're not gonna actually do this, okay? The other thing that you need to know is about the standard deviation, okay? So I'll let you read that for a second and try to digest it a little bit, and then I will do my best to explain it. If you wish to take a picture of this now, this is all the properties that we're gonna talk about on this page. The adjustment gets made that the standard deviation of the sample mean is smaller than the standard deviation of the population, and the way we make the adjustment is we divide it by the square root of the sample size. So for the problems in 6.2, we didn't need to know how big the population was. For 6.3, we need to know how big the sample is, because when we do our calculation, instead of putting the standard deviation into the calculator, you're going to put the standard deviation divided by the square root of the sample size. That's the only change that you're going to enter into your calculator. Okay. So here's what I mean by this, and this is also called the standard error of mean. So what this means here, all of this in yellow, when I was talking about the standard deviation divided by the square root of the sample size, that's this. And if you see this notation, the standard deviation of the means, that means it's the standard deviation of the sample means. This is the standard deviation that we use for the central limit theorem. Okay? It's just a bar over the top that means mean. Nope, no more to this. takeaway here is if you're dealing with central limit theorem, if you're dealing with samples, you're going to put this in for standard deviation in your calculator. Instead of putting the straight up standard deviation in like we did for 6.2, you're going to have to put the standard deviation divided by the square root of the sample size. It's going to be super easy. If you really want to see it as a pain, look at the examples in the book that does it without the calculator. And you have to find all the z-scores and all that stuff. We don't have to do any of that because of our technology.
Good. So the standard deviation of the like the red thing, that's...
Here is what the the central limit theorem actually is, okay? As the sample size increases, the shape of the distribution is going to look more and more like a standard normal distribution, okay? The smaller the sample size is, the less like a standard normal distribution it will look like. The larger it is, the closer to a standard normal distribution it will be. And again, the mean is still the mean. The standard deviation has to change slightly, okay? So here's how you're going to enter it in your calculator. So everything is the same as what we've done until we get to the standard deviation. And there's going to be one exception here that'll actually make it easier, and I'll talk about that in a second. But really, this is the exact same formula that you were using before for 6.2, except this was just the sigma for the standard deviation. It didn't have the square root of n divided by it. Okay? And again, that's the change in the calculation when you deal with the sample. That's the only difference. And so when I said at the beginning about a slight change in the calculation, that's it. Everything else is the same. Here is the first example. Feel free to take a picture of that. And then try to set it up. And just try to finish this problem. And let's see how you do. And don't get too hung up if it's not the best on your first try, and we'll correct it as we go. And like I said, most of what we're going to do in 6.3 is pretty straightforward. Pretty simple. There's going to be one little nuance, but it's not a big deal. There's only one extra piece of information here than the problems that we had in 6.2. And that extra piece of information has to do with the sample size. Okay? They tell us that we're administering this test to 22 students. Not every student in the world. Okay? In 6.2, we just assumed that it was given to everybody. So they gave us the mean, they gave us the standard deviation, they gave us our bounds, or said greater than or less than, and we just plugged that in the calculator that way. The only thing that you have to take into account now is the fact that it's a sample, and so we have to adjust our standard deviation based off of that sample. Okay? Square root. Mm-hmm. Square root of 22. So that's the only change that you have to make. Okay? Enter it all in your calculator without actually doing it. You can just put that standard deviation divided by the square root. So here's what you should have been entering into your calculator. Okay? My lower bound is 27. My upper bound is 31. The mean is 30. So none of that changes from what we did in 6.2. The only change we make has to do with the standard deviation. So instead of it just being 5, I have to do 5 divided by the square root of 22, that sample size. And then, and you can enter this, you don't have to find the square root of 22 first and approximate it as a decimal and then you can enter it into your calculator just like this. Okay? So in reality, again, and I know some of your calculators look a little bit different, but you can enter the standard deviation just straight in there. Okay? You don't have to do the calculation for the square root of 22. You don't have to do 5. You can enter it just like that, and it'll do the work that it needs to do. Okay? How many had that? You're dying to know if you got the right answer. should have gotten 0.8235 or 82.35%. How many had that? Okay. Now let's think about why that number. So one of the things I want us to start doing is examining the reasonability of an answer. Okay. Since 5 is the standard deviation, one standard deviation is 5. Okay. And we're talking about from 30. All of these numbers are inside that. This one is 1 away. This one is 3 away. So they're all within one standard deviation of the mean. And so we would expect to have a fairly large number, because if you remember the normal distribution, 68% is within one standard deviation. Because it's only a sample, we expect it to be a little bit different, and in this case it's a little bit different, 14% different. Okay? But it is close. How many of you had this? All right, let's look at another example. This one again, this is the only example, and then the next example there will actually be 2 on the page, and that's where the slight change comes from. So if you want to go ahead and do that one, go for it. Yep, I don't know. Good question. Let's fix that. How many got that? Okay. Huh? I told you it was easy. All right, 2 more things. 2 more problems. All right. So here is a lot of your problems are going to be like this. Okay? And this one, A, is where things change slightly, but not in a bad way, in an easier way. And I'm going to talk about that in a second. But go ahead and set it up. Just do A for right now. Don't do B yet. Do A for right now. What is the sample size for A? 1. Okay. A single egg is selected. Okay. So here's the nuance. So the sample size is 1. So let's think about that for a second. Okay. If you're trying to make a generalization about a population of something, and you only choose one thing to sample, it's going to be less accurate. Okay. But at the same time, the calculation is going to be more like what we did for 6-2, and here's why. Okay? Because I'm dividing by the square root of 1, which is just 1, it ends up being exactly the same as the standard deviation. So when the sample size is only 1, you actually use the exact same calculation as we did for 6-2. You are welcome to continue to write 15 divided by the square root of 1. It's just extra typing. They equal the same thing. But the reason, again, that's the one exception. When the sample size is only 1, the formula that gets used for central limit theorem is the same as what we did for population in 6-2. Okay? That's the only nuance to it. Just something to kind of point out. Can you still type it in like this? Absolutely. You will get the same answer and it's fine. But I just want you to know that the formula does change a little bit when the sample size is only 1. And it's because when you divide by the square root of 1, you're dividing by 1, which is the same thing as the number you started with. Which means, in reality, the formula is just standard deviation instead of standard deviation divided by the square root of n, because the calculations are the same. All right. So the number should have been 36.94%. How many had that? Okay, so go ahead and do B, and understand it's the same problem, except the sample size is different. So what you're going to see is that the probability changes quite dramatically. Okay, so again, the calculations, the only change here is the square root of 25, and if you feel like doing this calculation in your head and figuring out that it's 3, you're welcome to do that. You know, it's up to you, or you can just enter it straight in the calculator. That's not a big deal. Okay, but notice the difference here. Okay, it changes quite dramatically when you increase the sample. So just kind of keep that in mind. How many had that one right?
Me.
All right. That's 6-3.